Good morning, everyone. It's my great honor to be invited to join the Vebleo webinar. And my name is Zhanxi Fan. I'm currently an assistant professor in the Department of Chemistry at State University in Hong Kong. And today I will talk about our recent work on the crystal phase control synthesis of novel metal nanomaterials. My presentation will include the following 4 parts. Firstly, please allow I will introduce the background. So actually, my research work is mostly aimed for improving the catalytic properties of novel metal nanomaterials. Catalysis, as we know, it is quite related to our daily life, including the environment, energy, chemicals, and materials. Okay, so because of the unique electronic structure and also the excellent stability of the novel metals, so novel metal nanomaterials actually have served as an excellent catalysis for many important applications. For example, the catalytic converting of the they can serve as catalysis for the small catalytic converting of small molecules such as nitrogen or the carbon dioxide, especially the carbon dioxide electrocatalytic converting of carbon dioxide into some variable chemicals of the fuels. This is which is quite related to the carbon neutral and as well as the carbon cycle on Earth. But currently the change still lies in the preparation of the high performance novel metal nanocatalysis. So in order to increase the catalytic performance of the novel metal nanomaterials, actually great efforts have been devoted to the shape control over the past 2 decades. Okay, the shape control of the novel metal nanomaterials have been well achieved. You can see here many interesting there are many, okay, you can see here there are many beautiful or well-defined shapes of the novel metal nanomaterials. But all the crystal phase of all the nanomaterials actually they are different shapes. Actually, they are still limited by the FCC phase. That is the common phase for especially for the gold and palladium and also PT and silver. So currently, the crystal phase control is still in the initial stage. Okay. Actually, crystal phase actually is also one of the most important and fundamental aspects of the materials because the physical chemical properties of the materials is greatly depend on the crystal phase. Here, let's take the carbon as a typical example. For example, from the view of a chemist, actually the diamond, no matter whether actually both diamond and also the graphite actually is just a carbon, but actually with by changing the atomic arrangement of the atoms in the carbon materials, actually, for example, for the cubic phase, that is actually the diamond. Everyone likes diamond. It's very precious. Okay, and these materials actually the diamond is insulator and also is very super hard, and also it's a transparent materials. It's colorless. Okay, but in sharp contrast, actually for the graphite, that is a hexagonal phase of the carbon. It is a very good conductor and also it's very soft and it's dark color. So you can see the crystal phase can greatly affect the properties of the materials. So actually, beyond the carbon, actually for the novel metal nanomaterials, researchers have also found that they can also greatly affect the properties. For example, by changing the crystal phase of the FEPT from the FCC to the FCT phase, actually they can greatly enhance their properties, the chemical stabilities, and also their magnetic property can be totally changed from the paramagnetic to the ferromagnetic. Okay, and also the catalytic activity of the platinum nickel nanostructures can be greatly enhanced by changing the crystal phase from the FCC1 to the ACP. And also very recently, in our science report, Professor Ng Chaojin, and he observed that actually by changing the crystal phase of gold clusters from the ACP phase to the body center cubic phase, actually the carrier lifetime of the gold nanoclusters can greatly enhanced. Okay, actually it's enhanced by more than 4,000 times. Okay, so you can see the crystal phase control is quite important to modulate the properties of the novel metal nanomaterials. So how to realize the crystal phase control of the novel metal nanomaterials? generally, traditionally, actually, there are two pathways. Firstly, you can use a small heating method. In this method, actually, you can actually the lattice, especially the the atoms in the crystal lattice will be rearranged at high temperature. And also, there's another method that named it compressing method. In this method, and the high temperature at a high pressure, usually several tens of GPa, actually the atoms will be forced to be rearranged. Okay, and then you got another phase of the materials. So actually, these are for this. Although these two commercial methods are quite effective, but there's some drawbacks here because both of them involve very extreme conditions. That is the high temperature and also the high pressure. So actually, this is sometimes not wanted, especially for the ultra thin and anisotropic nanostructures. So in this case, so people are prefer to use some method that can realize the phase control and the mild conditions. For example, the wet chemical synthesis, but currently, actually, frankly, to say it's still quite a challenge. So in the following, I will talk about our research efforts to toward this research target or research goal. So first, I will talk about the one-particle synthesis of the gold nanomaterials unusual phase. Actually, gold nanomaterials actually it has been studied for a long time. Actually, over 1.5 centuries ago. It's for example here you can see here is a bottle of the gold colloids by the Michael Faraday, and he synthesized this kind of gold colloids. Okay, in 1857. So so actually later, especially in last century, with the invention of the transmission electron microscope, actually the a lot of new gold nanostructures of gold has been synthesized and observed. And you can see here other single nanowares and also polyhedrals and also gold nanorods, okay, and also the gold nanocase. Okay, but all the crystal phase, all these net structures actually they adopt most a FCC structure that is a somewhat dynamically stable phase of the gold. So actually, these are actually until the 1997, actually the scientists observed this unusual phase, or 2H phase. That is so for in the transmission electron microscope. So compared to the conventional phase, actually 2H phase demonstrate unusual stacking characteristic sticking sequence of AB along close pack direction compared to that of ABC for the FCC phase. So, but frankly, but actually, currently, the chemical synthesis of the angular phase or angular phase gold is still very challenging. It's quite difficult. So actually, in parallel, we also noticed that actually for the other kind of materials, for example, for the semiconducting materials, and also the metal porous materials, people can change the solvent system. And by changing the solvent system, it will observe that the crystal growth behavior and also the structure can be changed. So, bearing this in mind, and also we noticed that actually previously in the synthesis of gold materials, most people just use water or use unary or just use unary solvent system. So in this case, we propose that if we switch the system to the binary or ternary solvent system, maybe we got some unusual phase of gold. So by bearing this in mind, and we have explored a lot, and we finally found that there is a binary solvent system that involves an action and also 1,2-dechloropropan. And by using this kind of binary solvent system, we are able to synthesize a new crystal phase of gold. That is the 4H gold nanoribbons. And also for this kind of in this crystal phase, actually the crystal it shows a quite different stacking sequence. That is ABCB along the close pack direction, and from the TM image, you can see the ribbon shapes and also the electron diffraction, and also the cis-corrected stem image confirms the crystal structure. And also we have tried to study about the growth mechanism. First year we studied about the shift evolution, and we found that actually this kind of political ribbons actually initially actually they evolve from the ultra single nanowares, and later they gradually grow longer and also wider in the lateral direction, and gradually form this kind of morphology. But actually, we are most interested about the crystal phase evolution in this process, and we found that actually initial state, for example, at reaction time 4 hours, actually we observe some kind of short range twitch phase. Okay, and along together with the existence of some crystal defects such as staying force of twins structures. Okay, so later we observed that actually about the reaction time of 8 hours, actually the void phase start to appear, but this just a very short range void phase. Okay, and on later with further increased time over 12 hours, actually we got a long range void phase. Okay, so in this case, based on this observation, we propose that it's actually maybe there's a phase transformation occurred during the growth of this kind of unique void gold nanorobbins. Okay. And also by using the monochromated use, we are able to study the individual, the single nanorobbins of the void gold. So you can see here, we can map out the plasmonic resonance modes, okay, and also their intensity, their distribution along the individual gold nanorobbins at different energy losses, and also based on the use spectra, we are it shows that actually this kind of void gold nanorobbins, they have a very strong absorption in the infrared region. It can range from the near infrared region to all the way to the middle infrared region. That is, for example, here from 1,000 nanometers to all the way to the 5,000 nanometers. And also in combination with the theoretical calculations, we are able to find that it was observed that compared to this one, the FCC phase, okay, the void phase demonstrates less number of the plasmonic resonic peaks, and also all the peaks actually compared to the FCC phase are right shifted. Okay, so in this case, we provide a new way to modulate the modulate the optical property of the no metal nanomaterials through the crystal phase control. And also this strategy is quite general, and by further changing the solar system can easily extend it can be easily extended to the synthesis of another infrastructure that is heterophase for FCC gold nanorods. And also the yield you can see here is quite high. And also from the HRTM image, you can see the alternating distribution of the FCC and the void phases along the long axis of the gold nanorods. But for this kind of structure, actually, this kind of heterostructure, the void and FCC structures phases are randomly distributed in the structure. So very recently, by further optimizing the condition, actually, we are able to synthesize a new heterophase structure. We call it the well-defined heterophase FCC twitch FCC gold nanorods, because in this structure, you can see here in the figure E, you can see here, this is a typical dark field stem image. From this one, you can see that actually the two ends always FCC phase, and in the middle side section is always ACP phase. So that is the twitch phase. Okay. So in this case, actually the distribution of different phases in the structure is confirmed. It is determined. Okay. And and also the overall size is quite small, so it can have some applications in biorelated areas. And also the yield is quite high. And also we also use the monochromated use to study individual gold nanorods, and also this can be and also in combination with the theoretical calculations, we found that actually by through the synthesis of the heterophase gold nanorods, actually their peaks and also their intensity, peak position and also intensity just located between the pure FCC phase and also the pure twitch phase. So in this way, we found a new way to fine-tune the optical property of the no metal nanomaterials through the fabrication of heterophase, that is a heterophase nanomaterials, nanostructures. And also, we have also applied this kind of new phase structures for the CO2 reduction, for the catalytic CO2 reduction, and we found that actually this kind of structures, they demonstrate a much superior catalytic performance, catalytic selectivity, and also the catalytic activity compared to the FCC, the common FCC phase. And also they have very good stability. And so actually, besides the one-part colloidal synthesis, we can also realize the phase control of gold nanomaterials through the surface modification. So here, I would also introduce a brief introduction, give a brief introduction about the background. So here, usually, traditionally for the cross-packed metals alloys with FCC or ACP phase, actually the phase formation between FCC and 20 phase or ACP phase actually usually occurs through the motion of partial dislocations on the cross-packed planes, and also after the phase formation, the cross-packed direction is always is the same. Okay, there's no change in the cross-packed direction, and also after the phase formation, actually there's always a lot of crystal defects, and such as stacking faults, twins, and even the coexistence of the two kinds of crystal phase. So is there do the other kinds of phase formation exist? So actually it is still it is still under debating, and also in parallel, we notice that actually there is one report that is about the some report about the synthesis of the ultra-thin 2H gold score sheets, and also this gold score sheets has the thickness of very small, just around 2.4 nanometers. It means around 16 layers of gold atoms in the vertical direction. So in this case, the surface area to volume ratio is quite high for this structure, and also as a result, the surface energy will dominate the total system energy. So we propose that. So in this case, we propose that if we if we modify the surface energy, maybe we can trigger the phase formation. So here is about the scheme for the Lagrange exchange. Actually, we use the cell molecules to replace the oleamine molecules that initially kept on the surface, of the ACP gold score sheets. So actually, this Lagrange exchange can happen at room temperature. It is spontaneous because the cell strong interaction between gold and cell groups is much stronger than that of between the gold and the amino groups. Okay. So here, actually, interestingly, after the phase formation, we found that by using the TM and also STEM image, we found that actually the crystal structure has been totally changed to the FCC phase, and also the FCC gold score sheet shows a unique orientation of 100. So why we say it is unique? Because here you can see here from this scheme, I think it can better show you about what happens there. Okay, so actually the cross-back direction has been changed. You can see actually has been changed a lot. The angle between the initial direction, also after the phase formation, actually the angle is as large as over 50 degrees. So as we have mentioned at the beginning of this section, traditionally the phase formation between the cross-packed phases of metals and alloys actually after the phase formation, the cross-packed shape always keep the same. Okay, so here we observe. So it means that here I observe an abnormal or unconventional phase transformation mechanism for the cross-packed metals and alloys. And also we found that actually the concentration of the cell molecules is quite cool to this kind to trigger this kind of concentration, this kind of phase formation. And we found that actually low concentration will just result in a very irregular shift and structures, and also they have a lot of defects, and that means the crystal phase formation is not complete. And after actually, as the crystal concentration is 20 millimolar, as this concentration are all the above, actually we can go to where single crystal FCC gold score sheets. So, and also we have studied about the chemicals, different kinds of cell molecules. Actually, you can see here with different sizes of hydrophobic, hydrophilic, hydromertic, or dead cells. Actually, all these kind of cell molecules you can trigger such kind of ACP to the FCC phase formation. And also, so in this case, we confirm that actually that is a strong interaction between the gold atom and our cell groups. Actually, that is a key driving force to trigger this kind of phase formation. So in the past two sections, we have talked about the crystal phase control of the gold nanomaterials. Actually, so in the following section, the part 3, we will talk about I will talk about the temporary synthesis of the new multimetallic nanomaterials. So compared to the unary metal nanomaterials, actually multi-metal nanomaterials always have always show some better performance or more interesting properties because of the synergistic effects between different metal elements. So here, but currently the phase control of the multi-metallic nanomaterials is also a huge change. So here, usually for the synthesis of multi-metallic nanomaterials, actually two strategies, usually two methods. First, about one-part synthesis. Another method that is about the template groups. Usually for this template groups is sometimes preferred because they can have the better control over the structure of the final products because it separates the growth nucleation process and also the growth process. So in this case, we propose that if we use the interface metal nanomaterials as the template, maybe we can induce the formation of new multi-metallic nanomaterials with interface. So so bearing this in mind, we try to use the ACB gold score sheet as template to grow silver, and we found that actually in the present results, all the in present oleoamine can got just two kinds of structure. First, without the oleoamine, without the ligand, we can after the coating of silver on the 2H gold score sheet, actually these are similar to the cell induced phase formation. This is total phase formation from ACB to the FC structure, and we got the as a result we got 100 anti FCC gold and silver co-share score sheets, and also we found that if we introduce some lagging in the growth of the silver, in the coating of silver on gold score sheets, and then we can go the ACB and FCC gold and silver co-share score sheets. And also, besides silver, we can also code PT, but different to silver. Actually, in the case of PT, because of this much larger lattice mismatch and between gold and PT. So in this case, this also shape transformation, shape change from the score to the rhombic, along with the phase formation. So as a result, we got another unique structure that is a 101 oriented FCC gold and PT rhombic shapes. And also you can see here a lot of twins are formed in this kind of structure. And also by using this analyzing the cross-sectional samples with the stem, and also EDS, we confirm that the epithelial relationship between gold and core and the PT cell, and also from the EDS analysis, we can confirm this kind of co-share structure. And also, similar to PT, we can also, through the growth of PD on the gold, we can also get this kind of 101 oriented FCC gold PD rhombic shapes. So, besides the 2H gold score sheets, by using 2H gold score sheet as template, we can also use 4H gold and ribbons as template. You can see here, by using this 2H gold and ribbons as templates, through the epithelial growth of series of other metals, silver, PD, PT, and iridium, rhodium, osmium, and also ruthenium and copper, we can get a series angular phase, angular phase of these nanostructures. And also, we can also use this kind of, besides the unary metal, angular phase metal as by using the unary metal structure as templates. We can also use the bimetallic structures like the 40 FCC gold, silver, co-share nanoribbons as templates. In this case, we can utilize the galvanic reaction between the silver and the other metal salts, like the PD precursor, PT precursor, and also the in this case, we can get this kind of gold and PT silver, or gold and PT silver, the trimetallic co-share structures with the 4H FCC phase. And if we add the PT and PT precursor simultaneous into the solution of the containing the gold and silver nanoribbons, and then you can get this kind of gold and PT, PD silver multi-metallic nanostructures. And also, most importantly, this kind of angular phase nanostructures, they have some very unique, very excellent properties, catalytic properties. For example, we have applied this kind of the 4H FCC gold and PT silver nanoribbons for the hydrogen revolution, and we found that you can see here their performance is much better than the PD black, and also it's very close, or it is comparable with the PT black, and also they have a very high stability, very excellent stability. And also we have also used the 4H and 4H FCC gold and copper nanostructures for the electrocatalytic catalytic carbon dioxide reduction, And importantly, these kind of structures, they have a very much better performance than compared to the common FCC copper. And for towards the generation of the Asst, and it's one kind of very important multi-carbon products in the CO2 reduction reaction. And you can see here their selectivity and also their activity is both much greatly improved. Okay. And so here I would like to briefly summarize our recent research work or research findings. Okay, here firstly we have developed 3 kinds of wet chemical methods to for the crystal phase control of noble metal nanomaterials under mild conditions. And also in this process, we have discovered the new crystal phases for a series of noble metal nanostructures, such as for its gold, for its PT, for its PT, for its iridium, rhodium, osmium, ruthenium, copper, and also some alloying material nanostructures like PT silver, and also the PT silver. And also we have got some unique heterophase noble metal nanostructures. For example, the heterophase for its FCC gold, and also the well-defined heterophase FCC to its FCC gold nanorods. And also in this process, during this experimental studies, we also for the first time we have observed an unconventional phase transformation mechanism for the close-packed metals and alloys. And also all these unusual phase non-metal nanostructures actually they show some promising application in the catalysis, especially the carbon dioxide reduction reaction. And also that maybe in the future they can also extend to their application can also be extended to the other areas such as plasmonics and also some bio-related areas. So based on the previous studies, actually we have proposed this concept of the concept of crystal phase control in the review paper in the Crystal Chemical Society reviews. And also very recently we have summarized about the crystal phase recent work on the crystal phase in a special issue of the Accounts of Chemical Research. We have summarized the recent work on the crystal phase control of gold nanomaterials by the vacuum synthesis. You can see here, usually gold have FC phase. Currently, actually, a lot of many other unique structures, crystal phases have been discovered by our group, by us, and also the many other research groups around the world. Okay, and from this the timeline here shown here, actually you can see here, this timeline shows the development of gold nanomaterials over the past 1.5 centuries. Actually, you see here from the gold colloid synthesis by the Faraday in the 1850s all the way to the 2010. Actually, most of the gold nanomaterials actually they adopt the common phase, that is FCC phase. Actually, starting from 2011, and all the way to current research status. So actually, in the past decade, you can see here a lot of many kinds of the unusual phase golden structures has been obtained by us and also the other research groups around the world. Okay, so it is so lastly, I would like to take this opportunity to thank my supervisors, Professor Hua Zhang, and also Professor Haimei Zheng, and also Professor Bai Yang, and Professor Hao Zhang. And also I would like to thank my collaborators, Michael in AOS, Yuhan in Cost, and also Professor Lin Gu in the Chinese Academy of Science, and also Professor Bo Huang in the Polytechnic University of Hong Kong. And also thanks for the funding support from our university and the department, and also from the ASFC, and also our NPM Center, and also ITC. And also lastly, I would thank my students and for their hard work. And okay, thank you all for your kind attention. Yeah, that's it. Thank you.